It's been a while since we've done a video, so I wanted to create a video, maybe a series of videos where we ask you some questions, just to kind of get the world's perspective from your eyes. And so, Jonathan, if you could tell everyone how old you are.
I'm 9.
So, you're 9 years old, you're in fifth grade, and you like to study quite a bit on your own, learning lots of different subjects. And so, one of the questions I think a lot of adults struggle with is understanding space, like the size of the space. How is it possible that space can be so big, or even on the opposite side, how are things so small? How's it possible for something to be so small? So I guess I just wanted to ask, like, if you take something and you keep dividing it by a half, and then divide it again and continue to do that, how small can things get?
So, if you divide things in half, you'll slowly lose detail. At one point, you'd lose so much detail that the average human eye can't see it, but it's still the size of it's still the size where multicellular things can be there. Later, if you keep on dividing stuff, you get to atoms, and some people can even divide atoms themselves into protons, neutrons, and electrons, but those aren't even the end. You can divide those into quarks, which are basically the atoms for an atom. After quarks, you can't really divide, but in in matter, because quarks are the smallest matter, not atoms. Except quarks are theorized, not proven.
So how small is a quark? Like if you put them together?
If you, but you're almost a lot of quarks can fit on tiny spaces. For example, the top of for example, the average phone length in quarks is over a sextillion.
The length of it?
Yeah, in quarks.
I see.
Quarks are around one millionth of an electron, and an electron is one millionth of an is about is a very small very small section of an atom. And assuming that, then quarks are measured sometimes in yoctometers or smaller.
But what exactly is a quark?
A quark is a type of subatomic particle that has the ability to basically that has the ability to mimic some small different actions. For example, up quark, down quark, top quark. There are different sizes of them.
I see. So yeah, so things can get almost infinitely small. So like when you get to numbers, you take a number, you divide it by half, you keep dividing it by half.
You can do that a lot of times before people give up on the names.
So what's the smallest number, or is there a smallest number? There can't be a smallest
There's
number.
no really smallest number, except because you don't divide. Negatives can become a smaller number. Why else would -1 be lower than 0? So basically, the smallest number is basically the largest number, but in a different order. And no one really uses negatives or fractions to a high extent, but you can tabulate really high numbers. For example, 10 to the 100, or also known as a googol, is just the amount is a good estimation for the amount of possible games of chess.
So yeah, so the opposite of something being really small, I think, the concept of big numbers and big things, including the universe, can be pretty daunting, I think. So, how many people on the earth?
Just about 8 billion.
So that to me is a big number. But, when it comes to like grains of sand, how many grains of sand on the earth?
About 100 sextillion, I'm pretty sure.
So 100 what is it?
Sextillion.
100 sextillion. So that's such a big number. It doesn't mean
Basically,
much
10 to the 23.
10 to the 23. Wow. And so so when we were talking about the universe getting big, how many? So are there more grains of sand than planets or stars?
With current estimations, people have estimated around 100. I think it's 100 million in our galaxy, and there's 100 million galaxies. So putting all those numbers together, 100 million is technically 10 to the 8. 10 to the 8 times 10 to the 8 is 10 to the 16, which, converting back to actual numbers, is about 10 quadrillion, pretty sure.
That's the number
No, wait,
of...
10, is it 10 quadrillion or 10 quintillion? I think it's 10 quintillion.
That's the number of planets with the number of planets. So are there more grains of sand or suns, I guess? Or planets
Grains of sand, because there's a pretty high amount, except some people do argue on it. I see with my calculations that it's probably more grains of sand than planets, but some people argue that there's more stars than grains of sand.
And I guess, the whole even grain of sand is kind of confusing, because would one big boulder be considered a grain of sand?
Technically, if you did weather it like a lot, it would be like millions of grains of sand.
So you're even counting boulders in the grains of sand?
I wouldn't be. I'm counting every desert and beach.
Oh, okay.
And
so actual grains of sand.
Yeah. Not boulders, because grains of sand have to be smaller than a salt cube for me to classify it, because salt cubes are usually double the size. So usually the grains of sand, I'd say, have to be smaller than that. So pebbles, all those stuff, out of the equation.
So why do you learn this stuff? Why do you like to look up and understand all of this?
I just kind of have nothing else to do, because I get pretty bored easily. So usually I find something random, and as soon as I find it interesting, which is usually 30 minutes to an hour, I will study it for at least a month until I exhausted almost everything.
But you also remember it, and so I find it pretty interesting, the questions that a lot of people have. So like with the universe, to me, I try to understand how big is the universe, and if it's growing, what was there before, and if there was nothing there before, there had to be something there before, and if there's walls, you reach the end, then there would be a wall, but then in theory there'd be something beyond the wall. One of the things you had mentioned a while back is that all the atoms that exist they're not expanding, they're not shrinking. So essentially they're just the distance, they're spreading apart?
Yeah, basically, it's more like the universe is like a balloon inflating. If you draw multiple dots on it partially filled, blowing up the balloon to make it bigger would basically be the universe expanding.
And so how many atoms are there in the universe? So is there a finite? So there's a finite number of atoms.
As far as we know, there is, because if it's an infinite number, then the size is also infinite, but we can never prove it, because the furthest we could ever see is 13.8 billion light years away, and our estimates go as...
Why is that the furthest we can see?
Because the universe with detections to see how old it is, with estimates, says that it's 13.8 billion years.
Oh, that's like from the Big Bang?
Yeah, and the light could never travel further than that, because light would have to be going faster than light, but then the whole light year thing would change.
I see. So it can only be as big as the speed of light that things are traveling to expand outward.
Yeah.
Wow. And so what is that the fastest? What's the fastest thing in the universe?
Light.
So there's nothing faster.
Yeah, and most other things get pretty close. For example, electricity is only a few hundred meters a few hundred miles per second shorter in speed.
And then what does heat have to do with it? Like, what's the hottest thing in the universe?
The
are those
hottest thing
suns?
in the universe, it goes to many things. Stars can go to over 100 million degrees Celsius in the core, but on Earth somehow people got a 5.5 trillion degree temperature in Celsius by colliding billions of atoms together with speed basically about the same as the speed of light.
Oh wow! So that's what was that for? What did they? Are they
It
just
was
trying to figure out?
It was experimenting.
So they made a lot of
with
heat, but isn't
things.
that? I guess we're creating a lot of heat. Is that an explosion?
It can't really count because it wasn't really one. It's because and if anything was exploding for it, it'll probably be vaporized.
Oh, I see. And then is there?
Because it's not like even tungsten could survive in 5.5 trillion degrees.
Yeah, that's a big number. And so that's the hottest. I guess things can get super super hot, and I imagine the opposite's true. Super super cold.
Yeah, the coldest we've ever got is negative 293.1444.
What is that? The coldest
Yeah.
on the Earth?
Yeah, which is also the coldest in the universe because it was created in a laboratory.
Oh, in the lab.
Yeah. In fact, the
Wait, how
lowest
much was that? 200?
negative
That doesn't seem that cold.
293.1444. Brownian motion, a certain physics law tells us that the more energy something has in the term of heat, the faster the atoms are moving. And at negative 293.15 Celsius, the atoms are just there. They're not moving at all. And if it's like, say, negative 294 Celsius, then they would have to be moving in a negative speed, which you can try to do a negative speed yourself.
Oh, I see. So then there's physics limits based on atoms
And the
so on,
yeah.
on how cold something can get in the
It
universe.
also limits on how hot something is, except instead of being negative velocity, the atoms get so fast from Brownian motion that they travel at the speed of light, and at that temperature, you could imagine that nothing could get hotter because it would cool down eventually. But the temperature, to be specific, is 192 nonillion degrees Celsius. 1 nonillion is 10 to the 30.
Okay. I don't know all those big numbers. So you like big numbers, right?
Yes.
So I guess how do big numbers work? Because to me, I think a lot of people know what is Google. Then
Yeah.
I think that's about it. A Google is a one with 100 numbers,
yeah,
100 zeros behind
I
it.
asked most people in my class for the biggest number, and most of them answered Googleplex,
Googleplex.
which is basically the plex complex. It makes it like more further. So whenever you hear plex in a number, it's basically saying remove that one term of that plex, because because there's also Google Duplex, which is the Googleplex of the Googleplex, and you remove one term and basically experiment with that in some sort of way that makes it there. For example, Googleplex, the plex goes on Google, so that makes it so that Googleplex has Google zeros and Google has 100 zeros.
So that's very hard to follow.
Yeah.
But yeah, and then there's other bigger numbers than Googleplex.
Yes.
How big can they go, or are they named, or do you just say?
Most people do have names, except past a certain point, they it sounds like they ran out of names because the names you wouldn't want to name any object or
So that's kind of like
anything.
naming stars.
Yeah.
There's unlimited numbers of stars, so after a while
So
you just
after
start
a
naming
while
them.
you start naming them J4EB 607.
So then how many, or what's the biggest number that you know, and how do you know that?
It goes pretty far because I barely even studied for 10 hours. And I haven't memorized too many yet. If you can say that 100 isn't
So
too
you're
many.
memorizing big numbers?
Yeah.
What does that mean?
I'm just memorizing the number or what.
Because I can
or
say,
after a while the term and the name.
because I can say my number is 10 plus infinity. That's the biggest number ever, isn't it?
11 plus 10 plus infinity plus 1.
So then what are the names? How does that work?
Basically, people name it with multiple parts. Usually, there's 3 parts. There's plex, which basically, as said, makes things more complex and adds. There's extra prefixes, which do something, and they're way rarer. Some people change. For that, they either change the vowels in there because most of them have a lot of vowels. Examples, there's a lot of examples out there. And names, they usually base it off lower levels of names.
I
and
saw a strip of paper you created that had some numbers on it. What was that?
I was just doing something where I was like searching what numbers there were. Then I actually accidentally found this thing, and so the numbers became so large that I couldn't really understand them. So I compiled a massive list of large numbers.
And what, you cut those together and tape them to have a big strip of numbers?
Yeah. I'm working on an extension for this right now.
So what do they say? Like, what is it?
Basically, on this side here, it's the notation. And the reason why I say notation is because there's 5 main ones. This one has 4. And then we have the main names as we go down, which slowly get more and more obscure as you go down.
So, like, if we try to say how many atoms in the universe, what number would that be?
It would probably correspond in between vegentillion and tregentillion.
So that's the number of atoms, actual atoms in the entire universe.
10 to the 76 on here. If you add up 10 to the 63 and you could minus 76 and 63 to get 13. And you have trillion, which is 12, then you add a 10. So the lower bound of atoms is 10, I hope I'm saying this right, 10 tritrigentillion.
Wow. Yeah, no, it's just the concept of estimating the number. First off, estimating the number of suns, then the planets, and then of course you have a lot of other.
The upper bound on the other side is 10 to the 84, which 10 to the 63 plus 10 to the 21. Times would be 10 to the 84. So it would be 1 sexagentillion for the upper bound, which is bigger than the previous number by a magnitude of 8.
So this is not complicated for you, all these numbers and understanding
not complicated,
the universe.
except this evil notation down here took me an hour to understand.
Why? What's so complicated?
It has 4 numbers, and this is the main notation later. The 4 numbers basically go on this. So basically, the first number is the first part of this part. The second number, if you check up here, the second number would be so the first number is the start of this. The second number would be would be the end of it. The third number would be the middle part, and the fourth number would be how many times you'd repeat this function. And this function corresponds onto these ones, and those, of course, you have to learn even more things to actually get it into something you could understand.
So those
And
are
it took
really, really, really big numbers.
Basically an hour. And no one
Just an hour.
and no actual person would probably go below this part for numbers to memorize, because above here you quote unquote might have the tiny little chance that you could tabulate something with, I don't know, try a quintillion, or
Like what? Like the number of
the
code.
the number of you could do
Actually-
like the 10 to the 90 is basically the amount of the number is close enough. The real close one is in between here. You could tabulate maybe the amount of combinations of all the atoms in the universe, assuming we use the 118, which actually goes close to hectillion, surprisingly.
So for physics and chemistry and math, or all of those, you really need to understand kind of math.
Math
Ties it all together.
Math is a key part of science. Science is a key part of math. So if you start learning a small amount of math, then go with science, then math. Just alternate pretty much until you get to like maybe 5th grade stuff. Then they're more independent. Until 9th grade, then they're really tied together.
Because I met a really smart guy. I think this guy was kind of a genius on a plane one day when I was flying to San Francisco, and we were talking about you. He sat next to me, and I think you were still 5. And what he had said was that the entire universe is made up of elements, or atoms, essentially, that make up elements, and those are the key components that make up everything in the universe. And so to understand the building blocks of the universe, how they all work, how they interact, and so on, you'll pretty much be able to map out answers for every single thing that is out there.
Yeah, basically. And
so you already learned, or you already learned all the all the elements.
I remember I learned basically most of them, not all.
I mean, I guess there's some that are.
You not need to know protactinium unless you're a scientist or that's trying to discover a new atom for the very low prize.
But like something like salt.
Salt is, you not need to know the chemical composition, but in simple terms, table salt, the most common form, because there's Epsom salts, which are, and other types that basically.
But these are compounds, they're not elements, right? They're multiple elements.
They're multiple, because even air is not just, is compounds. The main one, except the only exception to them are noble gases, which gases that just like to hang around naturally. 1% of air is a noble gas. It's argon, to be specific.
Yeah, I find it interesting if you ask most people what is air made out of. Most people think it's oxygen.
It's mainly nitrogen. It's N2O with argon and CO2 and a lot of other weird things that I don't need to mention at all because they're not because they make up 0.0, like maybe less than 1/1000th of the part of the air.
And one thing that I guess I wanted to touch on, I thought it might be a little too abstract, but when we talk about the universe and the elements and the planets and suns, there's of course black holes and antimatter.
Yeah.
And to me, those are really hard concepts for me to understand because first off, the black holes can get pretty confusing when you think about how big they are, how little is known, and I mean just how can they exist, and they're eating up all the atoms and hiding them. I don't know. Again, if
Whatever.
something can't be, if an atom can't be destroyed, then what happens to it when it goes in a black hole?
It basically becomes the black hole. Little is known about them because we can't say we even discovered 100 of them, but let alone 1,000. And mainly we need a lot of them to see a lot of them to see what they actually do. And black holes, you can't see what they actually do unless you're the
But
person.
how big is one? Like, what do we know about black holes?
What we know about them so far, black holes have three main elements.
And where do they come from?
Black holes come from multiple places. They come from stars that are more massive that are very massive, that contract to such a dense point that it becomes a black hole. Other tiny ones came from the universe being born, which then it was so dense that something that's slightly denser than its neighbors could have became a black hole. And other sources include the middle of a galaxy, which most people don't know why, and it's not holding everything together. Dark matter is, which is basically...
Dark matter, is that the same as antimatter?
No. Dark matter is a type of matter that's basically invisible. And,
well, to me, almost everything's invisible.
and then there's dark energy, which is a type of is the opposite, polar opposite of dark matter. Dark matter likes attracting things. Dark energy, more than dark matter, pulls things apart. And dark energy counts for 63%. Dark matter counts for, I think it's 22%. No, it's more. And everything that we can just see, or quote unquote see, is 5%.
Really? So, I mean, what I find interesting is the universe, even though there's big objects in it, they're small in comparison. So, the universe is really just full of space. Actually, everything is full of just space, because within an atom, there's just a lot of
99.9999 countless amounts, like 1 over any number in between here that I'm not sure about
is space.
Is just empty space within an atom, which is surprisingly useful.
But that doesn't sound realistic, and I think, again, people have a hard time understanding, because if you can hold something and pick it up, how can it be made of space?
Because
99.999%.
Because most people don't know this, but you're not picking it up. You're actually squishing the air in between it to a point where the air is actually lifting it up, and you're lifting the air, which sounds really weird, but nothing can't be touching anything else.
I see, because atoms don't actually touch each other necessarily.
Unless it's something like a neutron star or black hole or anything that in that matter.
Wow. So what's your favorite thing to learn about? I guess it changes.
It usually is like a seasonal thing that changes every season. Right now it's studying large numbers, which is why I made this list that will only extend until I get to infinite numbers. Then I'll make a separate list. Then I'll do the very limit of numbers. Then I'll go into fictional numbers, which sounds weird, but I've explored like maybe part 5, like 4.5 out of 37 for big numbers.
So what's interesting, Jonathan, is you're 9 years old, and all of these things that you talk about, you just know all the details about them. You can reiterate the I guess, statistics and the numbers and so on. Make these calculations on demand in your head. These are, I think, very hard things for most people to understand, and you do it all for fun, basically.
Yeah, basically all of this was for fun, and if I printed everything else out, it would probably extend to like that long-ish.
So what do you find hard? What is hard?
Hard is my two things that I find hard is things that are super easy but take like really really long lengths amount of time.
Like what?
For like if like 6-digit multiplication, except if it was 100 times more time consuming. And then the other thing is, I don't know, high school, maybe even college level stuff, because it's not like I don't know what gravity is. In fact, gravity wasn't really invented. It was found by Isaac Newton, because whatever invented it was whatever created the Big Bang, which of course no one really knows what caused or created the Big Bang.
But I guess what you were saying is, if I understand correctly, that the things you find hard is not really understanding things, it's presenting it back in the manner that is being asked. So it could be time consuming, or it's being asked in a certain way, and that's the hard part. Is you may understand the answer, but they're not asking the right question necessarily, or they're not asking it in a way that makes it easy to answer, or maybe it's just not easy to answer, I guess, in the first place. But yeah, so this is really good, Jonathan. I want to do some more videos in the near future, and I think what we'll do is we'll ask other people, kind of like the way you asked ChatGPT some questions, and essentially everyone's curious, like, oh, how does ChatGPT know these answers, and they kind of impressed with the answer that comes out and so on. I kind of want to understand how you see things, what you've learned, because I think it's kind of interesting. All these concepts are very challenging, but for you, since you picked these up kind of naturally, you don't see them as challenging. They're just like, the sun comes up in the day and it sets at night. It's just easy for you.
It's just that.
And so it's kind of interesting to get your perspective on some of these, I guess, what I would consider challenging topics.
They're, in my opinion, just for fun activities.
Yeah. Okay, Jonathan. We'll make a video pretty soon.
Okay.
Okay. Bye-bye.